Last time we started numeration systems, and we had gotten through, well, tell me one of the numeration systems we did last time. Roman, we started. We didn't quite finish that one, right? Yeah, so we're going to talk more about Romans today. Who did we finish?
Babylonian.
Babylonian, we liked them. They had few symbols, but it's kind of complicated, right? Mayan. What's unique about Mayan that you remember?
They had the 0.
They had a 0. That's unique. What else?
Their first place was 360. It wasn't, even though they had a base 20 system, the first place was not base 20 exactly.
Okay, so not the first place, but it was the third place. Third, actually third. But yeah, so they had this weird modified base 20 system where it really wasn't 20 times 20. They did 20 times 18 somewhere. And they also were written vertically, right? That's very different. None of the other systems have that. There is another number system that I've taught before. It's not in this book. Chinese. The Chinese write theirs vertically as well. So that's kind of cool. Who else did we do? We missed one. We missed the one that's attached to my necklace.
The Egyptians.
The Egyptians. We did the Egyptians. We kind of like the Egyptians. It's easy to read and write, but it's cumbersome, right? We'd have to write a whole bunch of symbols if we had some 9s involved, yeah? Okay, so today we're going to pick up talking where we left off about the Romans. Who looked, be honest, who looked at Rayleigh Chapel's clock? Okay, a few of you did. Did you figure out what's weird about Rayleigh Chapel clock?
Actually, my brother pointed it out to me, even though we both went and looked at it. When they go past, it's probably, in the way they're trying to make it in a circle, some of the numbers are actually upside down.
That's true, but that's not what's wrong about it. What about the number 4, Tori?
It's 4 lines. Instead of 5.
Yeah, so we haven't done it yet, but you guys probably remember from outlines and so forth, thank you very much, that the number 4 should not have 4 eyes, right? But it does on Rayleigh Chapel clock. It has 4 eyes. So that's going to be our jumping in place for talking about the Romans today.
Why did they do that?
I don't know, but if you see it, it's not the only clock I've seen that does that. I've seen other clocks that do that too, for the number 4. I don't know why. I haven't looked at the number 8. I suspect the number 8, or not 8, 9, is probably right, because I think there's probably too many symbols for them to fit it in if they did it wrong. So, all right, so this is the subtraction property at play. Anytime that they wanted to avoid writing more than 3 symbols, they would put a smaller value in front of a larger one. But it's only one value smaller. So this will only affect 4s and 9s. Okay, it only affects the values that are 4s and 9s. So if we wanted to write 90, how would we write 90? Well, it's really close to 100. What's the symbol for 100? C. Whoops, that's the wrong color. I need a darker color on this backdrop. I need a C. And then it's exactly 10 less than 100, right? So how do I write a 10? X. So I put an X in front of the C, and that's the number 90, because this number is smaller than this one. Okay? Now, 99. You would be awfully tempted, I know I would, to write the 100 down and put a 1 in front of it. 1 in front of 100. But they don't do it that way, okay? They do it by place value. So as we're looking at this, we're going to be thinking about this as 90 and then 9. They write the 90 as the C with an X in front of it, okay? That gives me 90. And then how would you write a 9? An X with a 1 in front of it, actually. In front, yeah. So you'd get the 90 by writing XC, you'd get the 9 by writing IX, and then you would put them together. And that would be 99. Okay? Our goal is not to tell them, man, it would have been easier to write IC. That's not our goal. Our goal is to do it like they did it. Okay? So we're going to write it the way that they would have. There's another property at play, and I mentioned this last time. What about numbers bigger? Right? If you looked at this list of numbers, it stopped with 1,000. So what if you owed somebody $90,000? Well, that would be really bad, first of all, right? But you couldn't write it and write out 90,000s. That would be impractical. So they have one more property, and it's called the multiplication property. And what they do is they place a single bar over a Roman numerator to multiply it by 1,000. And if there's a double bar on top of it, it multiplies it by 1,000,000. So if we wanted to write the number 9,000, you kind of think of it as being broken into two pieces. Ignore the 1,000 part. Focus on the 9. How do you write 9?
X and
X and an I with the
I.
I in front. This is how you write 9. And the way you get it to be 9,000 is you put a bar on top. This would be 9,000. Everybody good with that? Okay. So we're going to take one of their numbers, MC, MX, and we'll get to the switching it up to what the number actually is with our system third. But first, we're going to figure out what number comes before MC, MX. What do we do in their system to get a number? Well, we look at the last place value on all of our systems. So the last place value here tells us what's at the end of this number. What's the X value?
10.
It's 10. So how do we get a number that comes before their X value? What comes in front of X? An IX, right? So if we were like writing them all out, we would have V, and then we'd have VI, and then VII. We'd get IX, and then I, and then we'd get plain old X, right? IX and then X. So the number that comes before X is IX. So the MCM stays the same, and it's IX to get the number before X. And what would we do for the number that comes after it?
Put the I on the other side of that.
Yeah. We'd have MCM, and then we'd have XI to get the number that comes after X, the XI. Now let's go back and actually change this into our number. So what is M worth? 1,000. What's the C worth? Just writing the numbers down for now. What's C worth? 100. M we already said was 1,000. And X is 10. Okay, so the only time subtraction comes into play is if a smaller value is in front of a larger one. And do we have that here? Yes, we have it right here. Yeah? So the smaller value is the C, which is worth 100, coming in front of the larger value that's 1,000. So what happens when we have 100 in front of 1,000? We get 900. So the first M is 1,000. The CM in the middle is 900. And then the X at the end is 10. And combined all together, this gives us 1,910. So we got to have one that looks a little bit more complicated with some of those lines that we talked about. This number is 1,000,000 something or other, right? Okay. So we already talked about if the number's big, and this is big because it's over 1,000, that we're going to sort of break it up like this. Okay. Now, there's two schools of thought on this. The way that we want to think about this first is the number in front of there, 1492. You know, that's from Columbus, right? 1492. Can I write that with the symbols that we have without having to worry about the fact that there's a million in here? Can I write 1,492? I can, so I will. Okay? So we're going to write 1,492. So how do I get 1,000? M. How do I get, whoops, sorry about that. How do I get 400?
500 minus 1.
Yeah, so this is going to have a subtraction property because it's a 4 or a 9. So what I want is I want a 500 minus a 100. So what is the 100 symbol? C. It will come before the 500 symbol. And what's the 500 symbol? D. So this gives me 400. The next number I have is the 9 for 90. So 90 would, again, it's going to be a subtraction property because it's a 4 or a 9, is going to be 100 minus 10, right? The 10 will come first because I need to subtract. So how do I get a 10? X. And how do I get 100? C. Let me move this down some. And then I have a 2. How do I get 2? 2 I's. But all of this is times 1,000. So how do I get this to be represented as times 1,000? One single bar over it. Now, if I didn't have the 019 at the end, I just had 000, we'd be done. But I do have the 019 at the end. So how do I get 19? Well, one place at a time. How do I get this 1, which represents the number 10? How do I get a 10? X. And how do I get a 9? IX. And you'll notice this number, part of it is underneath a bar and part of it's not. That's okay. We can do that. Okay, everybody good with that? All right, I left something else in my office. I will bring it next time, but it relates to base 10 blocks. You guys have probably seen base 10 blocks before, but I'll bring some for you just so you can see them again next time. Base 10 blocks are a super cool manipulative. They're very simple to help kids understand addition when we have more than one unit or more than one numeral. Okay, so when kids start in kindergarten, first grade, they're adding, you know, like 5 plus 7, right? But as you get towards the middle of second grade, it's sort of looking more like 15 plus 72, 2-digit numbers, yeah? Well, this helps with that 2-digit kind of addition idea. So these are the manipulatives that we're going to talk about. They're called base 10 blocks. A unit is a small square, is what it actually looks like, is a small square. Ours is going to look very two-dimensional on here, but it is actually a 3-dimensional object, of course. The way that you get along is you attach 10 of these together, okay? So it looks like the same width or whatever as the unit, but it's going to be long. It's 10 of them stuck together. So imagine like Legos, right? Stick the 10 little Legos together and they make a long Lego set, 10 long. A flat takes 10 longs and sticks them together to be a giant square that's 10 by 10. And then a block sticks flats together, 10 of them, to give you a cube. That's a terrible picture, but you get the idea. It's a cube. It's called a block. Now, in base 10, which is the comfortable base that you're known to be familiar with, everything is exactly what I said. A long is 10 long, a flat is 10 longs, and a block is 10 flats. So you get base 10, that this is 1, this is 10, this is 100, and this is 1,000. And it becomes very clear as to why I can't take a long and a block and say I have 2, right? One long and one block can't be added together. They're not the same size, yeah? That's why this helps kids to see the difference between the place values, is because the sizes of these objects are different. You can use money the same way, right? Pennies, dimes, and dollar bills. Unfortunately, we have lots more coins and things like that, and the size doesn't always really help us, because if you look at pennies and dimes, it's not real helpful, right? The size is not there to be quite as helpful as the blocks are. Now, what we're going to do is recognize that we do not have to use base 10, okay? So we're going to change the bases that we use as we're thinking about this. So this is 1, 10, 100, 1,000, because it's all by base 10s, 10 squared, 10 cubed, and so forth. But what happens if we were doing base 8? In base 8, how much would a unit, a long, a flat, and a block be worth? Now, a unit's always worth 1, so you get that one for free, okay? So a unit is worth 1. How much do you suppose a long would be worth? It'll be worth 8. It'll be worth 8. How much do you suppose a flat would be worth? 64. And you get that, Rebecca, by doing 8 squared, right? Exactly. And then what would we do for a block? Yeah, we do 8 cubed, which is 64 times 8. Does anybody have their calculator out for us? 512 is correct. That's how much the place values or these manipulatives would be worth in different base, in particular base 8. So if you considered these manipulatives and you had 2, 3, 7, and do you see the little tiny little word 8 down beside it as a subscript? That tells you that this would be base 8. Okay? In this case, we can talk about it in terms of blocks. So thinking about this 2 would be 2 flats. It would no matter what base you have. 3 longs and 7 units. And the question is, how many individual units is this? How much is a flat worth?
512 units.
That's blocks.
It's much. That's
Yeah.
64.
64. A flat was worth 64. Whoops. Better. A long is worth what? 8. And a unit is worth what? 1. And if we add together the 2 times 64 plus 3 times 8 plus 7 times 1, what do we get? You're close. What'd you get? 159. Yeah. Okay, so here's the image you want to have in your mind. I referenced Legos a minute ago, and I'm sure that at that point you automatically had an image of what this would look like if you stuck Legos together, right? Okay. So imagine then that you did that you brought in a bag or these Legos that are all stuck together, and you had some Legos that were all stuck together, and there's 64 of them all stuck together. And you've got 2 of those images with 64 Legos, right? And then you had some images that had 8 Legos, 3 of them that had 8 Legos stuck together, and then you had a few 7 left over. Now imagine taking all of those Legos and breaking them all apart into their single Lego component. You'd have 159 of them when you're done. Can you picture it? Another way to think about it is this one works really well for crayons. Because you've seen the 64 pack of crayons, right? You've probably all wanted it at some point or another. I know I did. It was just like super cool. 64 pack of crayons. You've also seen 8 packs of crayons, and you know what single crayons would be. So imagine that you brought in 2 packs of 64 crayons, and then you brought in 3 single packs of 8 crayons, and you had 7 extra crayons, and then you dumped all the crayons on the floor. How many crayons would you have? 159. Okay, so everybody have a picture of what we're doing here when we think about this. It says, question B above is equivalent to asking what 237 base 8 would be in base 10. That's what we're doing when we're breaking them apart like this. Now, before we go on too much further into the next question, can somebody talk to me a little bit about where you've seen other bases used on a regular basis, or maybe examples of it, maybe not on a regular basis, but you know of other bases that are used in our world today? There are several. Nobody knows any?
I don't think this would be one, but considering that maybe one presidential term is 4 years instead of, I don't know.
Yeah, I don't think that works quite like what you're thinking. The one that would come up if I asked this to a group of science students, is that they would tell you that binary. Who's heard of binary? Does anybody know what binary is? Do you guys know what it is when I say binary? What would you say that it is, Sabrina?
It's the zeros and ones that a computer uses to make the images.
Excellent. So in computer programming, zeros and ones are used, 0 and 1 because it's off and on. Zero's off, one's on. So it's really easy to turn things on and off. And so zeros and ones are used, and that's binary. That's base 2. Another computer language programming system will use something called hexadecimal. Hexadecimal is base 16. Okay? There's one that you guys use every single day.
It's time, isn't
Yeah. How many minutes are in an hour?
it?
60. How many seconds are in a minute? 60. It's a base 60 system. And then we get weird because then we have 12 hours and, 24 hours in a day, but we do our clocks with 12s, which is weird too. That's another issue aside. But you use base 60 every single day, don't you? Does anybody know why we use base 10 or why that's a common use of that? Like why we would want to use base 10? You've got 10 fingers. Yes, you do. Okay, thinking along that lines, why do you think the Mayans used base 20?
Because you have 10 fingers and 10 toes.
Yes, they did not have closed-in shoes like we do, correct? Yeah, they didn't. So fingers and toes. My brother likes to make fun of what I do, and he tells me that my students will be better if they don't wear shoes to class. He's a comedian. So, I can count on their toes. We talked a little bit about the Mayans as well and why they changed things up with their modified base 20 so that they get that 360 showing up, that weirdness right there. If you didn't have any thumbs, what base system do you suppose we would have probably used? Base 8. Probably would have used base 8. All right, so we're going to do a few other things with some number systems. Again, this is the part especially of this particular section where the whole point, maybe not the whole point, but at least part of the point is to make you feel a little bit uncomfortable, okay? So if you feel a little bit uncomfortable, you're in good company. Probably everybody else in this class is in the same boat, okay? So the first thing we're going to do is we're going to write down the numbers in different base systems. And I chose 3 random base systems, 3, 7, and 12 here. So base 3 will have the digit 0. They all have the digit 0 and 1, okay? So we're good with that. Now in base 10, what is our biggest digit? Single digit. 9. Okay, so there's not a digit for 10 in base 10, right? So we will have a 2 in base 3, but we will not have a 3 in base 3. Okay? In our system, when we run out of single digits, that is, when we've gotten to the end of counting to 9, we have to increase it to a 2-digit number, correct? And that 2-digit number starts over with the number 1, followed by the number 0. And the same thing will happen with all of our base systems. 1, 0, because we ran out of digits. There are no more digits. There's 3 digits in base 3 because there's 10 digits in base 10 and there's 8 digits in base 8. So what do you suppose comes after the 1, 0? And I will say 1, 0 because it's not 10. Okay, it's 1 and a 0. What would come after 1, 0? Not yet. 1, 1, and then 1, 2. And then I've run out of digits again, right? There is no 1, 3. So what would come after 1, 2? That would be your 2, 0, Rebecca. Good. Okay, we're going to go a little bit further up just so you can see. What's after 2, 0? 2, 1, and then 2, 2. And that is the biggest 2-digit number in base 3. So what would we have to do?
1, 0, 0.
You'd have to go to a 3-digit number, 1, 0, 0. And the process would continue. Right? That's a never-ending process. Okay, let's think about what happens in base 7. What is the smallest? 0, and then I've got 1, and then how far am I going to go with single digits? To 6. So I've got 2, 3, 4, 5, and 6, and then I run out of digits and I do 1, 0, all the way up to 1, 6. And then I have 2, 0, and so on. How about base 12? Base 12 is different than 3 and 7. What is different about base 12?
You do have a 10 and there with 1, 0 stuck in every 3 to 12.
Yeah, I need more digits than base 10, right? Yeah, I mean in base 10 I only had 10 digits and it stopped at 9, so what do I do next? Well, let me show you what your book does next. So we're going to go 0, 1 all the way up to 9, okay? So write the 9 down. For the number 10, I need a single digit. Agreed? I can't write 1, 0. It's going to have another meaning. I don't want a 2-digit number. I need a single digit number. What your book does is it writes T for 10. and it writes E for 11. And we're done because this is base 12. There's nothing else needed. If you did go on to 12, it would use a W. This is not my favorite way of doing it. There's another book that I have used. It's the one for contemporary that your brother's taking. And what they use in that book is they use A, B, C, and I think that's a little bit better than this because eventually I get to 13 and now I need what? Something else that's not a T because I already used T, right? So, but we're going to do what your book does, so we're going to do it this way, T for 10, E for 11, and if you needed it, you would do W for 12, okay? They don't go any bigger than that, though, so you don't need to worry. What happens if I have base 15? They don't do that, okay? Base 13 is as big as they actually seem to go. What do you suppose happens after E? That's my last single-digit number, because 11 is 1 less than 12, right? So what happens when I run out of single digits? I would get 1, 0. And I would go all the way up to 1, 9, and what would happen after 1, 9? 1 T, and then 1 E, and then 2, 0. And we would continue our way up. All right, so we're going to continue much like we did with the other numeration systems. We're going to find the number that comes before, the number that comes after. So these are the two that we're going to do. We're going to do one of them in base 5. We didn't talk about base 5, but what digits are in base 5? 0, 1, 2, 3, 4. Okay, so you already know how to do base 5. Okay, so the goal is to find the number that comes before the number that comes after. And there's no 5s or 6s or anything bigger in base 5. So what would be the number that comes before 1, 4?
1, 3.
1, 3. And you need to make sure that you write the subscript word 5. If there's no subscript written, it is assumed that you are in base 10. Okay? So if you're not in base 10, make sure and write which base you're in. 1, 3. And so if we were writing, it would be 1, 3, 1, 4. And then what would come after 1, 4? 2, 0. Because there is no 5, so I can't have a 1, 5. Make sense? Okay. We have T00. This one is a base 12 problem. One of those numbers up here was easy. The other one was a little weird, right? It isn't what it would have been in base 10. The same thing is true for this one, T00 base 12. Which one's easy, the before or the after? The after. What comes after T00? T01. Base 12. Make sure and write it. The one before, that's weird. So think for a minute with me. What do we do in our base system? What would we do if this were a 9? Just in base 10, if this was a 9. What would you do to get the number that comes before? You would essentially subtract 1. And in subtracting 1, what happens to the first digit here? It goes down 1, right? So let's do the same thing with our T. What's the number that comes before T? 9. Now, we know that this answer is 899 for the example that I sort of threw in the middle here. What happens to the zeros when they become 9s? What are they changing to? Yeah, they're changing to the largest value in the base, right? That's really what happens in our system. When we take 1 away from 300, it becomes a 2 and then a 99 because those are the largest values in our base. So if we're looking at the base 12, the next values should be the largest values in that base, and Catherine's right, those are E's because we're in base 12, so these are 11s. So this is 9EE, base 12. Okay, so that's what we did in our numeration systems for all the Babylonians and Mayans and Romans and everything, is we took one of these numbers and we said, what comes before, what comes after? That's exactly what we did, right? My first questions A and B in every section was like that. Question C told you, okay, now turn that number that's in that weird base that's not ours into our number. That's what we're doing next. we're going to take whatever random base we're given and we're going to turn it into our base 10 number. And you do this with multiplication. Please write multiply here. This is all about multiplication. So the first thing that you do is you put the numbers into expanded form. This looks a lot like what I did here. This is expanded form of the manipulatives. I wrote flats, longs, units. Okay, that's expanded form. It's what does it mean in context of what's going on. And then, oops, I even did it on the slide. And then I multiplied, right? For whatever each of those were worth. So we multiply out the expanded form that we have created. So here's a couple examples. So the first thing that I usually do is I write these numbers spread out with place value lines underneath them to help myself remember what the place values look like in this base system. This is base 2. They all have a ones place, the units place on the right. And then whatever base I'm working with will be the base of exponents next. Base 10, I have 10, 10 squared, 10 cubed. But this is base 2, so I have 2 to the first, 2 to the second, 2 cubed. We're working in base 2, so the powers are base 2. And truthfully, guys, this is a power of 2 as well. Right? It's 2 to the 0. So it's not like it's different. It's just that it's always a 1 no matter what the base is. So we can write it as a 1. So when we're writing this out in expanded form, we write the value that's in the place times the value of the place. So I have 1 times 2 cubed, 0 times 2 squared, 0 times 2 to the first, and yes, I know they're all 0, but just for sake of being thorough, I'm going to write them down so I didn't think I forgot anything. And then I have 1 times 1. So this first step really is to write it out in expanded form. I expect to see at the very least this step. You don't have to have the lines and stuff I did before. It helps me to organize my thinking, so I do that. If you don't want to do it that way, it's okay. But I do need the line where the multiplication is written out. And then you're going to actually multiply it out and add the sums together, or add the add-ins together for the sum. So if you don't know them already, you can write out what the values are. 2 cubed is 8. 2 squared is 4. 2 to the first is 2, and then 1 at the end. Multiply and add. What do we get? This is 9. If you want to write the base 10, the word 10 beside the 9, like this, you can. Just so that you're like, I'm always going to write one. Don't want to forget I'm always going to write one. But if you don't write it, it's okay. It's understood to be base 10 unless you've written something different. Okay, so I got to do another one with base 12 because that's super fun. Okay, so we got base 12. I have a T, I have a 0, and I have a 0. It's the ones place. So in base 12, what is the base of my exponents? 12, because it's called base 12, right? Yeah. So this is 12 to the 1 and 12 squared. Now we got a letter here, T. How much is T worth? It's worth 10. So I have 10 times 12 squared plus 0 times 12 plus 0 times 1. And does anybody know what 12 squared is? 144. The others are actually zeros, so we're kind of done with them really. You don't have to write down that step that I just wrote, but you do need to write down the step that I've got the arrow by up here, the one with the powers of 12. What is 10 times 144? 1,440. Okay, so changing some other people's base into our base is always multiplication. I would strongly encourage you to have that nearby as you're working on these. I would strongly encourage you that when the time comes that you write that on your note card. Because undoubtedly somebody will do the processes backwards because they forget which one goes in which direction. If it's multiplication to turn base question mark into base 10, What do you suppose it's going to be if we turn base 10 into another base? Division. So this is all about division. We are going to divide. So step 1 looks a lot like step 1 for the other one. Figure out what the expanded form of these numbers are, whatever base is that we're working to get it into. And then you're going to use the division scaffold, which we've done before, because we did it with our other numeration systems. So here's the imagery you've got in your head. I always like to dump things out on the floor, not literally, but figuratively when I get here, okay? You guys are super creative, and you decide we're going to do this cool crayon project. I like crayons too. In my classroom, or marbles, or blocks, or Legos, whatever you'd like. And you come in and you bring in 11,028 of this object, and you dump them on the floor in here. And you're going to organize them, because I kind of like organization. So you're going to organize them in some fashion. And the fashion in which you're going to organize these today is about base 4s, okay? So what does that mean? Well, it means that every bag is going to have in it some power of 4 number of pennies, quarters. Boy, that'd be a lot of money. Let's not do quarters. Pennies. I think that's still a lot. Maybe we'll do Legos or crayons. So we need to know what the powers of 4 are to make this happen. So that's where we start. We know we've got the first place value, which is a 1, and we've got the second one, which is a 4. Now, we can write down 4 squared, 4 cubed, but that's not going to be especially helpful at the moment. So it'd be more helpful for us to really figure out what is 4 squared and 4 cubed and so forth. So 4 squared I know is 16 and 4 cubed is 64. After that, y'all have to help me out. What comes after 64? 256 sounds right. And you can actually just multiply by 4 to get the next one, right? This is a geometric series. So 256 times 4 is what?
1,024.
1,024. And we will stop when we get a value that's too big. What's 1,024 times 4?
4,096.
And what is 4,096 times 4?
16,384.
Okay, I ran out of space, but it's okay because 16,000 is too big because my number's only 11,000, right? So I don't need this one. All right, so the biggest value I have will be the first value I divide by, 4096, and it goes on the outside of my division scaffold with the number I'm dividing, 11,028, underneath. And we've already gone through this process. You know what to do. I need to know the whole number part. 11,028 divided by 4096, how many times does it go in? Whole number times. 2. And then I need 2, just 2, times 4096.
11,028.
You just did times it again. I just need just the number 2.
I'm sorry.
That's okay. So just the 2 times 4096.
8,192.
Excellent. And then we will subtract 11,028 minus 8,192.
2,836.
Okay, 2,836. And we go down the line. What comes before the 4096? What is the next one on our list? 1,024. So how many times will 1,024 go into 2,836? 2 times. And 2 times 1,024? 2,048. And we subtract 2,836 subtracted or minus 2,048. Okay, so what comes before 1,024? 256. How many times will 256 go into 788? 3. What is 256 times 3?
768.
Excellent. And if we subtract, we get 20. Now, I know it's really tempting to just ignore the next one, but we will not ignore it. We will write down 64. And yes, I'm fully aware that it will go in 0 times, and that 0 times 64 will be 0, and that's all okay. Okay? We still need the 0 as a placeholder. Just like when we didn't have placeholders in these other systems and it caused problems, we need the 0 to be a placeholder in our system. If we keep going down, I've got a 16 now, so 16 will go into 21 time. Probably don't need your calculator anymore. 20 minus 16 is 4. 4 goes into 4 one time. I know that leaves me with 0, and you might be tempted again to stop, but you can't stop until you divide by the last value, which is 1, and I get, of course, a 0 at the end. So there's two things that tell me I'm at the end. I've divided by 1, and I've got 0 as a remainder, okay? Both of those things will have to happen before you're finished. But here's the coolest thing about the division scaffolding, especially with what we're doing here. The answer is right here. And you're done. Well, you're going to write it out. But it's 2, 2, 3, 0, 1, 1, 0, base 4. Okay, so let's go back to the image of all the dumped out whatevers in our classroom. We're going to say crayons. I have 2 bags with 4,096 crayons. I have 2 bags with 1,024 crayons. I have 3 bags with 256 crayons. Don't have any bags of size 64. 1 bag with 16, 1 bag with 4, and 0 left over. That's the image. Okay? We have one more example. We should have time enough to finish it, and then we will do group work for this next time. You don't have to do this over the weekend to start with, okay? You're welcome to start it, but don't do the group work. We'll do it here. Oh, I think that was just like a blessing in disguise, wasn't it, Abby? Okay, good deal. Glad to be a blessing today. All right, this is base 9, and we see lots of 9s, and we know that there are no 9s in base 9, right? Let's figure out what we have of our values in base 9. I know I have the 1's place and the 9's place. What comes next? 81. What's 81 times 9? 729. What's 729 times 9?
6,561.
Okay, and what is 6,561 times 9?
59,049.
Good. And we could go one bigger, but you probably looked at that and knew that that's big enough. My number's 99,000. This is already 59,000. Any bigger is going to be too big. So in our division scaffolding, 59,049 will go on the outside with 99,999 underneath. And of course it goes in one time. So if we subtract 99,999 minus 59,049, wow, I'm writing really large. Let's make that a little bit smaller. I'm going to run out of space. Okay, what do I get when I subtract that? 40,950. And then we will divide by our next value, power of 9 down, which is 6,561. How many times will 6,561 go into 40,950? 6. 6 times 6561 is what?
39,366.
Excellent. And if I subtract that, what do I get?
1,584.
Excellent. The next value to divide by is 729. How many times will 729 go into 1584? 2. 2 times 729.
1,450.
Good. We subtract.
126.
My next value is 81. 81 will go into this one time. So what is 126 minus 81?
43.
Good. How many times will 9 go into 45?
5,
And 9 times 45 is,
45.
and I get a 0. Am I done?
No.
No. Still have to write the division by 1, which I know, of course, I get a 0 out of it, but I need the division by 1 as my last step to have my place values correct. My answer, right here, is 162150 base 9. I want you to take a look at something before we stop for today. One real quick thing, but it's important. In base 10, this number had how many digits?
5.
There were 5 digits. There were 5 nines in a row, right? When I moved it into a smaller base, how many digits are there now? 6. That has to make sense, that there are more digits, or at the very least that the digit would look sort of somehow bigger, because I have fewer digits to actually be able to create my number with, right? I only have 9 digits instead of 10 digits. So if you go back and you compare every single time the base was bigger, so this was base 10, 11,028, and I made the base smaller, base 4, I got a bigger looking number. Bigger base, smaller number. Smaller base, bigger number. Okay, that always happens. You can look back over here. We had in base 2 is 1002. 4 digits in base 2 was 1 digit in base 10. Yeah? 3 digits in base 12 is 4 digits in base 10. Okay, so it's a good check step at the end to make sure that you converted it in the right way.